Hello everyone. Last time we talked about the gene expression dataset, and I want to review everything and continue what we were doing. Okay, so I'm going to import all the packages and the path to my dataset and the gene dataset. I'm going to create the CSV data, and what I want to do actually here, I'm going to create gene names, gene exp _org dot I look all the rows and the first column. So I want to choose the first column, which is the gene names, as a separated variable, and I want to name it gene name. So now gene exp _org dot, I'm going to drop this column, gene expression org dot columns 0. I'm going to drop this from the data set, and I'm going to in place it means I'm going to right away change the data set, the original data set. So now gene expression _org, I want to see the data set very quick. Here will be the data set. Well, access equal 1. Okay, so we have samples in the columns and the genes are on the row. So let's look at the gene names. This is the gene names here. We can change the gene name to array using 2 numpy, and now we have just array of gene name. To convert gene column to an array. Okay, so what else we want to do? We want to standardize the data set. If you remember, by standardizing data set, we want to set the mean of all the data to 0, and the standard deviation will be 1. Standard scalar, and I'm going to fit underline transform the gene expression org. Okay, so I have created an we created a new data set, which is standardized, and all the values will have mean 0 and standard deviation 0. Let's see our data set. Standard, oh, that should not be. Okay, so what we did here, now I just remembered, we haven't imported any packages. So I'm I'm going to import all the packages that I need for this lecture here. And okay, so I have noticed something that I wanted to share with you. So sometimes the Python will, especially when you are working with Anaconda, it's going to tell you this package is not defined, or the package is old, or this kind of, for example, attributes is not from a certain package. So what you should do, you should update all the packages in your Anaconda environment. And after you update all the packages, you are going to reset your Anaconda, and you are going to run it again, run the Jupyter Notebook to be able to get the packages correctly. And it's always nice to search a little bit before you do anything. If you have any specific error, maybe it's just a special for your to your system, and I don't even know what's going on. So you should always search the error. Copy paste exact same error you receive on your computer, and then Google it. There are lots of Stack Flow form that can help you to figure out how to fix the problem. Now that we standardize the data set, we are going to create well, you know what I should do here? I'm going to create a new variable and call this gene expression scale, because sometimes it's getting confusing, so it's better to have a proper name for this. So to see our data set, actually we already copied this, so I want to see this as a data frame. I'm going to create pd.data frame and cut this scaled and say the columns are the gene expression. Do you remember we went through this before? So I'm going to get the columns name for the original package and assign it to the column name for this pandas data frame. Okay, so let's see. This is what it looks like. It shows all the samples name as a column, and we created a data frame here. Okay, so the next step is to perform PCA. How we do that? So last time also I showed you, but now I'm going to separate the PCA, and then I'm going to fit the PCA separately in this way. So I'm creating an object of PCA, and then I'm going to fit this object. So I have gene expression, and then look at this. I changed this to a scale, so we know that this is a scale data set. We are going to fit this, and then we are going to print some of the characteristic of this PCA function. One is the explained variance ratio this is ratio and then the next one that I want to print is the variance itself. So this time I'm not going to print the ratio, And then the next one, I'm going to print the cumulative sum. So if you remember, cumulative sum will add each of the variance for the first one to the next one, the first two summation to the next, and then first three summation to the next. It's going to find the cumulative summation of these explained variance. So what we are going to do, we are going to write down NP cumulative sum, and we are going to use the PCA ratio to find the cumulative summation of these PCA. Again, when we have a star there, means it's taking its time until it loads. So if I print each of them in a new line, we have a nice output. Okay, so why we need explained variance? As I explained before, we want to see which PCAs are explaining the most of variability in the data set. And then as we see here, based on cumulative sum, the first three PCA are explaining 86% of the variability in the data set, and for us 75% is still a very good variability. So we will choose those PCA that explain the variability of data set very well. So what I'm going to do, I'm going to create a cumulative sum as a variable itself, and I want to just print part of this cumulative sum. How many of them? Just maybe 0 to 8 of them. I think in previous note I showed 7 of them. Okay, so we will see up to 8 or 9, 8 of them, 8 of the PCA explain the variability up to 90%. So we are good. So there is one graph in PCA analysis. They call that a scree plot. So what this does, this will show the variability of PCAs in order, so we can have a better look at PCA data and realize which one we are going to choose to explain the data. So we use PCA transform. I hope I wrote it down right. And then we are going to use gene expression. What was that? Scale data, right? And so what we are doing here, we are using PCA of scale data to get the some information to draw a plot using this PCA of transform data, PCA transformed of scale data. So how many PCA I want to choose? Number of PCA, let's say, first of all, number of PCA is always less than the number of a variable, less than or equal to the number of variables. So let's see, number of PC, let's see how many PCA we have from our data set. So remember, we have like 2,500 44 columns which are sample, and we are considering them as a variable, right? And then here, number of PCA. Okay, now what's going on? Oh, here. So number of PCA will be, equal to the number of variables we have in the data set. Okay, so what I want to do now, first of all, I don't want to show all the PCA, because as I mentioned, I want to show those PCA that are explaining the data set very well, right? So I'm going to comment this out and say I want just 8 PCA. Okay, you can choose just 3 of them, 4 of them. As I said, 75% is still good. So to do this, to make a kind of fancier graph, I want to create PCA labels, which is kind of using strings. So I'm going to create PC string, PC, and then using str I, and creating a for loop I in the list of. Okay, so first of all, what I'm going to do here to show you what list does. So list of range, what I'm doing is creating some numbers. List of range 1 to the number of PC plus 1. Okay, if the number of PC that I was selected was 8, so now what list is going to print? It's going to print all the number from 1, because I said range from 1 to the number of PCA plus 1, right? So because range doesn't print out the last number here, because the last number is excluded, we have to have plus 1 to be able to print out the last number. So I'm going to copy the whole thing here. So what this means, I'm generating numbers, which is I, from 1 to 8. And then all this 1 to 8 goes to this parenthesis. So what happens? It will create PC 1, PC 2. So for I from 1 to 8, it's going to print out 1 to 8 in form of a string. So it will write down a string of 1, which is 1, a string of 2, which is 2, and it will attach it to this one, right? If I had a space here, it would print out PC1, PC2 with a space, right? Now it's going to print out PC1, PC2. So this is the way we can create some string and make labels. Okay, so now I'm going to create explained variance as a variable. And what I'm going to do, I'm going to round some number. Which number? These are the explained variance that I'm going to use and round. So in here, I'm going to paste this, and then I'm going to multiply the numbers to 100, and I'm going to keep these to 2 decimals number, right? And then I'm going to print this out for you so you know what we have. And then here also I'm going to print this one. I'm going to print this one as well so you know exactly what we have. Eight is included. Okay, so as you see, we have created a string of PC1 to PC8 using this. We created string of PC1 to PC8, right? And then what this one does, it's going to get all the explained variance, gets all the explained variance, multiply them by 100 and round them by 2 decimal points. So and now, because I don't want all of these variance, I just want the variance for the first 8, right? Because look at this, the explained variance for the last PCs are 0, right? So I'm going to replace this variable by all the numbers from 0 to 8. And I'm going to print this. Okay, so we have all the variance, and then I'm going to print actually this after it, right? So now you will know. These are the only variants that we are interested. Well, actually this is not good, right? So, okay, that's fine. Let's keep them. Okay. So now what I want to do, I want to create the graph. The scree plot. Here the title was a scree plot, right? I'm going to write down steps to a scree plot. And then what I'm going to do, I'm going to use plot. So this is math plot. So plot bar, the X, R, the range. Now you know, and you should remember, range will print the numbers from this value we write down to, now if I say length of exp var, means what is the length of this? Length of this is 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So length of variance, that variable, is 8. And then because I want to print out, to get all the number from 1 to 8, and we know if I don't add 1, this one will be excluded, so I have to add 1 to keep the 8 as the length of variance. Okay, so this is the X of this bar plot. What is the height? Height of each bar is the explained variance. And then tick label. So now this is going to be all the labels that we created, this one. So tick label are the labels we created. Here is the graph that we created using the explained variance. So as you see, the first PC will explain 70%. As you see, the height is the frequency or percentage. And then slowly the rest of PC will explain the variability less and less. Okay, so I'm going to make this plot fancier by adding X labels and Y labels. So what are the X labels? Actually Y labels. Y labels are the percent of explained variance and then X labels are the principal components. Correct? And then what is the title of this graph? The title is a screw plot. So screw plot shows us the variance, the explained variance in the okay, so why labels? Why did I add S? Okay, good. So now we want to look into the component loadings. So before that, there are something I should explain. So in PCA analysis, we are relying on some of the kind of concepts that comes from algebra, linear algebra. For example, eigenvalue, eigendecomposition, or eigenvectors. So eigen itself means own or self. And then eigendecomposition is a method to decompose a square matrix into its eigenvalues or eigenvectors. Now, what is eigenvector or eigenvalues? For example, for a matrix which is, let's say, called A, matrix A, we can write a formula like A V equal to I don't know how we write down lambda multiply V. So V is the eigenvector of V is the eigenvector of matrix A. So if A is a square matrix, and then the lambda here is the eigenvalue. And so if matrix A is multiplied by a vector and the result is a scaled version of the same vector, then it's an eigenvector of A, and the scaling factor is its eigenvalue. So let me write it down. So if matrix A is multiplied by vector V and it results in a scaled version of the same vector. So this is the scaled version of the same vector. So what this means, if matrix A is multiplied to vector V and it's equal to the scaled version of vector V, then what happens? Then it is an eigenvector of then V is an eigenvector of A, and the scaling factor is its eigenvalue, means the scaling factor which is lambda. Okay, so when we have n eigenvalues in PCA analysis, that means we have n components in a PCA analysis. So n PC component, right? And choosing the number of components will be related to the amount of variance. That's explained how. The explained variance ratio is determined with the eigenvalues divided by the number of variables. So the explained variance ratio is determined by the eigenvalues divided by the number of variables. So the explained variance that we got is coming from the information of eigenvalues for this matrix, a square matrix we have for our, as a data set. So what we are willing to do, we want to use the eigenvalues that are greater than 1. And this is actually not a rule, but it's better to have a eigenvalue greater than 1, which is a kind of higher than average. It shows it's higher than average. Okay, so now I want to create a covariance matrix. How? First of all, I want to create covariance matrix. So now what I'm doing, this is the steps to find the eigenvalues and eigenvectors. So how I should create the covariance matrix, let's call this covariance, and I'm going to use NP, and I'm going to use dot multiplication. So I'm using dot multiplication, which is especially for the matrix. So I'm going to say gene expression, and then what was that? Scaled, right? Dot T. So what this does, this is going to create a matrix transpose for us. And then, so I'm going to find the dot multiplication of matrix transpose of gene scaled and the gene scaled itself. And then what I'm going to do, I'm going to divide this multiplication by the original matrix I had, row of original matrix I had, minus 1. So the row of original matrix is going to be extracted using shape the index 0, right? Shape shows the row multiply column as a tuple, and 0 shows the first index. So let's see what's going on here. Good. So this is going to be the matrix, covariance matrix for us, right? And then using covariance matrix, what I'm going to do, I'm going to extract the diagonal matrix, diagonal of matrix, and the diagonal, and again we are going to use the transpose of that. Now we can use the regular multiplication, NP identity of gene expression, and then again we are using the original shape, and this time we are using the column. So if you look up how to find variance covariance matrix, there will be formula on internet. You can see the formula, compare with this, and you will realize how I got the variance covariance matrix. And diagonal of this matrix also is going to be computed with a formula, and if you Google it, you can easily see the formula says use the diagonal transpose of the covariance matrix and then multiply that to the number of column. Look that up, you will see. So let me show you what this says. This is a matrix that shows just the diagonal of the gene expression. Original is 1, the rest is 0. So imagine matrix transpose of this, multiply a matrix that has a diagonal equal 1. Okay, so I'm going to find a correlation matrix now using NP dot, and then again inside this I'm going to use NP dot, and I'm going to use diagonal square T inverse and variance covariance matrix. Well, let's name it inverse because this is the inverse, and let's keep them equal. Okay, so NP dot of this one, and again diagonal square inverse, and this is going to give us the correlation matrix that I'm going to print it here. This is a correlation matrix between each component. Actually, we can use this to draw a graph as well. So let me continue what I wanted to do. I wanted to get the eigen value and eigen vector equal to NP dot linal g dot eig eigen of the correlation matrix. And what I'm going to do, I'm going to print this too. Okay, good. So actually I'm not satisfied because let's print them separately. Print eigenvector, and then I'm going to write down eigenvector, and then eigenvalues. Okay, good. So now explaining about covariance correlation matrix. So we need this covariance correlation matrix of this data set to apply the eigen decomposition. I explained about that. These are all the methods in linear algebra, and eigen decomposition, eigenvalue, eigenvector, these are all related. So we can use both the variance covariance matrix or correlation matrix but we can, use the best one. And which is the best one? The correlation matrix is the best one. Why? Because the correlation matrix, correlation itself is a unitless measure, right? Because correlation is based on two different variables. Imagine correlation between height and weight. So height has a unit of measurement, weight has a unit of measurement. Correlation between these two will be a number, but this number will not have a unit of measurement because it cannot choose between, for example, height and weight, right? So correlation is a unitless measure. So now correlation matrix is also a unitless measure then. And that gives us a better chance to be able to have a kind of freedom of unit changes. And as you see in gene expression data set, we didn't even see the unit, right? We even don't know sometimes what is the unit that we are using in the gene expression data set. And sometimes standardization will help, but using correlation matrix and finding eigenvalues is helping us to prevent any mistake or error caused by something like unit of measurement. Okay, so in another word, whatever unit of measure we have for our data set, we get the same correlation overall as a correlation matrix, but we cannot get the same thing for covariance matrix. So again, in conclusion, correlation matrix is always better when we are calculating this kind of data set, analyzing this kind of data set. So we use correlation matrix and apply some method like what we did to get the eigenvalue and eigenvector. And as I explained before, the eigenvalue and eigenvector are also related to the explained variance of each component. Okay, so I will come back with the rest of this lecture shortly. Take care of yourself.